In this lesson, we shall focus on applied mathematics APM3711. We shall be looking at numerical methods too, looking at a wide range of techniques we use to solve numerical problems in applied mathematics. And we proceed as follows. To start with, we shall be actually trying to discuss some of the very important notions that pertain learning. And the kinds of questions we are discussing are examinable questions. And therefore, they are questions that must be learned for purposes of exam preparation. We start by looking at this particular question, and often than not, it is expected that students must be able to explain why the numerical solution of a characteristic value problem of the type u double primed plus f of x u primed plus k squared u equals 0 with the initial values u at 0 is 0, u at 1 equals 0 by the method of finite differences leads to an eigenvalue problem. Here, f of x is an arbitrary function of x. Here, f of x as it appears in the differential equation is an arbitrary function of x. But we are saying the numerical solution of the characteristic value problem of this type by the method of finite differences leads to an eigenvalue problem. We need to explain why this leads to an eigenvalue problem. And this is how you must be able to discuss this notion and give an explanation that is satisfactory in this case. And this is how you're expected to discuss this. And we start as follows, and we say, we have, of course, what we call the characteristic value problem is given. It is a second order differential equation. And as it is a second order differential equation, to answer this question, we start by saying characteristic. Right, so characteristic value problem. Right, characteristic value problem. U double primed f of x u primed plus k squared u equals naught. U at 0 is 0. U at 1 becomes 0. Right, so to actually therefore seek to explain this in the kind of detail, we must take note of the following. In parentheses, we note that obviously this problem here has the trivial solution where the function u becomes identically 0. Right, the function u becomes identically 0, and therefore this problem in general is expected to have a solution that is identically 0 for certain. Right, for certain values of w. Right, values of w called characteristic values, called characteristic values. However, we note that actually in this discussion, it may also have non-trivial solutions. Okay, we know that obviously it's a trivial solution, but it might also have non-trivial solutions. Moreover, solving. We know that solving the characteristic value problem consists of finding these characteristic values. And usually, right, we know that indeed, and usually, finding the corresponding right, finding the corresponding solutions as well. Right, finding the corresponding solutions as well. Okay. We reiterate that fact and elaborate on this, and we are really saying we call this the characteristic value problem. That's what we call it. And this problem has the trivial solution where the u we try to solve for, because obviously solving this second order differential equation will mean solving for u and finding the function u as a solution to this differential equation or the characteristic value problem. But this problem has the trivial solution u identically 0. Now, for certain values of w called the characteristic values, it may also have non-trivial solutions. In other words, we may also have what you call non-trivial solutions to this. Well, I mean, it is clear that since this differential equation equals 0, if ever u equals 0, you plug in 0. The second derivative of 0 is 0. The first derivative of 0 is 0. F of x times 0 becomes 0 plus 0, 0. If u is 0, 0 times u squared, 0 times k squared becomes 0. As a consequence, then we have 0. In other words, it is clear that this particular homogeneous system has u as a trivial solution. Has u as a trivial solution. And the word trivial suggests an obvious 0 solution in mathematics. So trivial means 0 solution. So for certain values of w called the characteristic values, it may also have non-trivial. So in other words, not only that we might have trivial, but we might have non-trivial. Solving the characteristic value problem consists of finding these characteristic values. Right, so we may actually be in a position to find non-trivial solutions. And as we're indicating here that for certain values of w, right, called characteristic values, and these characteristic values, we shall determine them. We shall give examples of the characteristic values w we're talking about. It may also have non-trivial solutions. Solving the characteristic value problem consists of finding these characteristic values. So I'll find them, these characteristic values w, and usually finding the corresponding solutions as well. On top of finding characteristic values we call w, but finding the corresponding solutions as well. Now, to actually elaborate fully for the 5 marks, we will take note of the following, and this is how we'll approach the problem. So let us assume that the grid points, okay, you shall understand the grid points very soon because you shall give examples of what we mean by the grid points. Let us assume that the grid points Right, we assume the degrees points are T subscript I and let UI be the approximation. Be the approximation for U subject to or as a function of Ti. So let us assume that. We assume that the grid points are Ti and let UI be the approximation of U of Ti. Substituting. Substituting finite. Right, there is this technique of substituting what you call the finite difference approximation. Right, so substituting finite difference approximations for the derivatives. U double primed and U primed most certainly leads to a linear set of equations. For the UI. We moreover realize that substituting finite difference approximations, well, we shall see what we mean by this substituting the finite difference approximations because we shall do examples today. For the derivatives U double primed and also we have the derivative U prime leads to a linear set of equations for the UI. We continue to discuss the fact that this set of equations can be written in the matrix equation right of the form. Okay, you can write it in the form A minus, can write it exactly in the form A minus B k squared I times U equals 0. And this is given for some matrix A, right, for some matrix A. So the kinds of questions are examinable questions we're discussing, but we shall always indicate exactly where they came from. Right, so this is true for some matrix A and a real number. And the real number B, right, B element of R where U is the vector, of the UI values. Okay, we are effectively then reinforcing the fact that this set of equations can be written in the matrix equation of the form A minus bk squared, I in brackets times u equals 0 for some matrix A, and real number B, element of R, where U is the vector of the UI values. And obviously the U being a vector of the UI values, which appears outside the parenthesis, becomes the desired solution in this case, and we can be able to solve this. Once again, we shall give examples of these in this particular discussion today, so that you can see the finite difference method, at least in action. Okay. We also make the following indication. In brackets, we note that here, there's something called the difference equation. So here, the difference equation will be will be 1 plus h over 2 f of xi ui plus 1 h squared k squared minus 2 u subscript I plus 1 minus h out of 2 fxi u primed I minus 1 subscript equals 0. So basically we're saying, and actually so, in fact, our B becomes equal to h squared. Our B therefore becomes equal to h squared. Okay, we're saying here the difference equation will be this. Okay, you shall see exactly how we're able to transform using the finite difference method to how we can transform the given equation to this particular one. Right? And so when we note that, in fact, B becomes equal to the B that appears in the matrix equation becomes equal to h squared. And the h squared is what appears in the difference equation. And this becomes our difference equation. Now, once again, it will be clearer with examples than the statements we are giving. However, we explain further to say we need to find values of the k squared that appears there. So in this case, we then are saying finding, for example, finding the values of k squared such that a non-trivial solution, right, which is a vector. We saw the vector u outside the matrix equation because the matrix equation contains vectors as solutions. And now we're then saying find non-trivial solution vector u exists. Right, so this exists is therefore equivalent. Is therefore equivalent to the problem of finding the eigenvalues of A. Also, it is actually the case with the corresponding. With the corresponding eigenvectors. Giving the non-trivial approximate solutions. Okay. Moreover, it is not true that we are using right. However, it is not true that we are using the eigenvalues to solve the equations. It's a word of caution. We actually note that, as we've elaborated, it is not correct. It is not appropriate to say it is not correct to say to actually say that we solve the matrix. Okay. I see a language warning there. Or that the set of equations can be written as a matrix. As a matrix. As a matrix. Right, so we are actually making mention of the fact that that it's something that has to be, as a matter of fact, noted there. Right. Because we solve a matrix equation, we actually have seen that we convert this differential equation to a matrix equation like this, and we attempt to therefore solve it. And we are able to write it as a difference equation of this form, and we then can be able to solve for the u in this case. And we shall give examples in this case in which the finite difference method, or what we call the method of finite differences, is used to solve at least one differential equation or several differential equations. But first, we look at the following questions. First, we look now, we want to look at how we study matrices in this module, but also how we use them, because we spoke about matrix equations and how we use them to solve certain problems. Now, the matrix A, which has the first row minus 2 and 2, the second row 1 and 1, has an eigenvalue near near minus 2.5, and another one near 1.5. Right? Use the power method. So we want to discuss the power method to find the eigenvalue near minus 2.5. Do 3 iterations starting with the vector 1 and 0 transpose. Okay, so we look at these carefully. The eigenvalue. Right, so the eigenvalue so there will be a couple of eigenvalues that are most certainly involved here. And in this particular question, we look at the fact that the eigenvalue near, right? There's an eigenvalue that is near minus 2.5. So the eigenvalue near minus 2.5 has the largest magnitude. Has the largest magnitude. So we can find it by applying the power method. By applying the power method to the matrix A. Right, to the matrix A. So we look at the dominant one, we say, right, to the matrix A. As usual, we shall use the word dominant eigenvalue. And now the dominant one is the one of the largest magnitude. Obviously, if we're saying there's an eigenvalue near minus 2.5, another one near plus 1.5, we can see that the one close to near minus 2.5, its magnitude is big, it's large. So we can find it by applying the power method to the matrix A that has been given. And we continue with the following examination as follows of this particular matrix value problem or eigenvalue problem. What you call the power method. Okay. The technique becomes as follows. Minus 2, 2, 1, 1. Now, if you take this vector and you put 1, 0, if you multiply, okay, we start with the vector 1, 0. So we therefore multiply the matrix A by the vector 1, 0. So it is the matrix A multiplied by the vector 1, 0 transpose. Okay, because it's the transpose that we're talking about, therefore we can look at this vector as a column vector than just a row vector, because it was just given as essentially a row vector. Now we're gonna actually make it a column vector. And now we then take the matrix A and we multiply by the column vector, taking the transpose of it, and we have 1, 0. Equals this. Row by column multiplication is minus 2 by 1. 1. Row by column is minus 2 by 1, 2 by 0. Minus 2 by 1 is minus 2, 2 by 0 becomes 0. So yeah, we need to multiply this row by column. But minus 2 by 1 is minus 2 plus 2 by 0, which is 0. And therefore, you have minus 2 as the result. And multiplying row by column, using row by column multiplication 1 by 1 becomes 1 plus 1 by 0. 1 by 0 becomes 0. And therefore, we have a 1 there. Now, we perform the following algebraic strategy. 1 minus 1/2 So what we do in light of the fact that this vector we're starting with is a 1, 0 vector. 1, 0 vector with the entry 1. What we do is we factor out -2 to create a vector that sort of simulates that. And therefore, you would have the 1 and -12 there. Next, we continue with our multiplication. And next, we do the following. And then we have 1 minus 1/2. Okay, now if you multiply this with that, you have -2 minus 1. So you have 1 minus 1/2. Like that. And moreover, we want a 1 there. So you'd have -3 factorized outside, which is 1 minus 1/6. Like this. Okay, so we factored out -3 to achieve a 1 because this is a 1, 0 vector. So we want these vectors to have 1 as the topmost entry, and therefore the bottom entry will be arbitrary, therefore. Next, -2, 2, 1, 1. Well, that -2, 2, 1, 1 is the matrix A, and we're multiplying it by the previous vector. This. And what are we getting? This by that. You have -2 times 1. It's -2 minus 1/3. What is -2? And the 2 times -6 is like -1/3. So we have -2 minus 1/3, which is the same as what exactly in this case. Right, so if you have -2 minus 1/3. Right, so you have -7 out of 3. Right, and remember, make sure we get the correct answer. So we multiply these things here, and yeah, it looks like we really are most certainly on track here. Okay, good. Yeah. Right, now when you multiply these with that, you'd have, for example, 1 by 1, which is 5 out of 6. At this point, you factor out still 1 to 1 here. So you're going to factor out -7/3. And if we do, you'd have a 1, 5 and 14. Okay. Now we have this. Now you have this. Okay. Now would need a negative. Right. You agree that if you factor this out, then you would need a negative here. Let us check this out and multiply. Okay, if you multiply -7/3 by 1, you get -7/3. But if you multiply -7/3 by this, so let us check that out. So you multiply -7/3 by -5 and 14. So this becomes exactly plus, and therefore 7 goes how many times into 14? It goes 2 times, giving us 5 out of 6. And we are right. We are right. So this is correct. But if you factor out the -7/3, then we'll get indeed -5 out of 14. Because they said we must do 3 iterations. Do 3 iterations. Now we have already done the 3 iterations, and we're able to make the following conclusion. Based on the 1, 2, 3 iterations, which follow the multiplication of the matrix A by the starting vector, 1 and 0 transpose. we're able to make the following conclusion, that at this point, the eigenvalue is approximately lambda equals minus 7/3. This is it. We're able to then see that the eigenvalue is approximately lambda equals minus 7/3. Right. That is what we have. And so having done this, is this answer correct or not? So you would actually be able to see that this answer would be minus 7/3, but there's something we want to do here. Okay, wait a minute. There's something we want to do to test this answer. This answer will say screen, and then we're going to come here. See where I've put that. Think I've not launched that. It's okay. Right, but now I will mention that. So you'll see, therefore, that this is, for example, minus 2.33 recurring. So that's sort of the estimate result. Okay. Okay, all right. Right. So once again, somebody can do the answer with decimals. And if you do the answer with decimals, then you'll be able to see that the result will be a minus 2.33 recurring. Why? Because somebody can come here and say, I want to do everything with decimals, and doing everything with decimals will entail what? Will entail trying to achieve a 1 here, and therefore dividing this by the same number, in this case, minus 2, and also dividing these by the same number, getting, for instance, minus 1/2, and therefore it's minus 0.5. And realizing, therefore, that at this point, if you continue and you extract and you use decimals like a minus 0.5 and another equivalent decimal here, and using these decimals, one can get minus 2.3 recurring, in which case, therefore, I mean, that would be the same result. It will be considered the same answer. Right. So, however, you would recall, this is the end of the answer, must indicate. But there is a note. A note would be that, in general, you would recall that A minus lambda I2 would be the matrix A, 1001, which is minus 2 minus lambda, 2, 1, 1 minus lambda. So you'd have minus 2 minus lambda, 2, 1 minus lambda, and then 1 minus lambda. Oh, just 1 here. Okay, so you'd recall that, well, in general, in mathematics, it's possible to write this, you know. From this, then we find there's something we then call the characteristic equation, which we then say we can then find the determinant. Okay, just a note on this, and there's a reason why. I will explain why I'm just writing this note here. You then have the determinant of the A minus lambda I2, but you can write also with the vertical bars. which is you multiply these things out. Okay, if you multiply, you get this. If you multiply, you get this. Okay, you try to find the determinant of this. This is concept I'm trying to drive towards. And normally we make this 0, but always we make it 0. Always. For eigenvalues. So it's not that we're just doing this, but we do it whenever we are determining eigenvalues. Okay, because the matrices sometimes we're going to deal with are like large. But yeah, I know that this one is just 2 by 2. So it's small. All right, so multiply this out. Minus 2 plus 2 lambda. Minus 2 equals 0. Lambda squared plus lambda. Minus 4 equals 0. Okay, now what would this be? So this would be lambda equals b squared. All right, because minus b plus or minus the square root of b squared minus 4ac out of 2a. This is the standard quadratic, giving us lambda equals minus b, the square root of the following. Okay, I'm going to explain why I'm just giving this note here and why I'm just giving this. So something that minus 4 equals 0. Right, so you'd find, therefore, that this one is going to be, yeah, it's going to be exactly the b squared, yeah, it's going to be 1 squared. For a is 1, c it's a minus 4. I know this, very well out of 2a. A is 1, which is minus 1 plus or minus the square root of 17 divided by 2. Lambda, if you do this, then you find 2 values. Minus 1 plus the square root of 17 out of 2, or lambda. Okay. Okay, out of 2. Using a calculator, you'd get 1.56 here. And here you'd get minus 2.56. Minus 2.56. In which case, therefore, you're going to see that indeed these eigenvalues that are given were indeed correct. The minus 2.56 and that. So, and the power method that we've used in this case, these are the actual eigenvalues which were given. But by virtue of the power method with the starting vector 1 and 0, we're able to find the minus 2.3. This minus 2.33 recurring is once again very close to minus 2.56. But now we know that using the power method to find the eigenvalue near minus 2.5 was, and we did 3 iterations. It was justified by the fact that the eigenvalue near minus 2.5 has the largest magnitude. So we can find it by applying the power method to the matrix A. To the matrix A. So we have the following. So we're done with this question. So we used the power method to find the eigenvalue near minus 2.5. And we did 3 iterations starting with the eigenvalue, starting with the vector 1, 0, and these were the steps. And therefore we're able to conclude that the eigenvalue is approximately the minus 7/3, which is close to indeed minus 2.5. And we are done with the first question about on the power method. And then we look at the next question. Right, in the next question, we're looking at the matrix B. Rather, in the question B, but the matrix A, which has minus 2 and 2, 1 and 1, has an eigenvalue near minus 2.5. Still, it's the same instruction. Another one near plus 1.5. Explain how you can use suitable shifting with the power method to find the eigenvalue near minus 2.5 with fewer iterations without having to find the inverse of any matrix. Right. So we're looking at this here. There are a couple of things we're going to take into account here. So we need to explain for 9 marks how you can use suitable shifting with the power method to find an eigenvalue near minus 2.5 with fewer iterations without having to find the inverse of any matrix. Okay, many times we need to find the inverse of the matrices. We're going to discuss that. But without having to find the inverse of it. We shall explain now. We shall do examples on finding inverses with this power method. Let us explain the suitable shifting. So we know that in shifting, right, we consider, right, we consider the following, right, right. Okay, we'll continue, please. Right, in shifting, we consider the matrix. The matrix B, which can be written like so, whereas is a suitably chosen number. Then the eigenvalues of B are and if lambda 1 and lambda 2 where okay, to understand, we'll discuss this, where the eigenvalues of the matrix A. Shall discuss this and make sure that it's pretty clear. This actually is what you call the method of shifting. Right, or suitable shifting. Okay. The power method. The power method requires fewer iterations if the magnitude of the largest eigenvalue is not too close to the magnitude of the second largest one. So in shifting, we consider the matrix B because we just want to discuss the method of shifting, but it is an explanation that is worth 9 marks. These questions repeat. So it's very important, obviously, that you pay particular attention to them because they repeat. It's not that we decided to do these questions. So there are certain questions that we're going to do, and these are very important, and they repeat. So you need to just make sure you can take note of these. Practice them. How to practice them? You write them down many times until you sort of can make sense of this. But is the word says it is shifting. What does it mean to shift? Okay, to change the position of. Right, so in shifting, you consider the matrix B, which is now A minus Si, where S is a suitably chosen number. Then the eigenvalues of B are lambda 1 minus S and lambda 2 minus S. If lambda 1, lambda 2 were the eigenvalues of the matrix A, right, so through the method of shifting, if we then are able to determine the eigenvalues of the matrix A like we did, and we find them to be lambda 1, lambda 2, then through shifting, we then can just minus S. Right, so we just put the S there, and we consider the matrix B that is formed by A minus Si, where S is a suitably chosen number. It's not just any number, we're just saying it is the matrix A minus S times the identity, 2 by 2 in size in this case, but it is a suitably chosen number. Then the eigenvalues of B become lambda 1 minus S, lambda 2 minus S. If lambda 1, lambda 2 once again, were the eigenvalues of the matrix A, the power method requires fewer iterations like we've seen. If the magnitude of the largest eigenvalue is not too close to the magnitude of the second largest one. Okay. The power method requires fewer iterations if the magnitude of the largest eigenvalue is not too close to the magnitude of the second largest one. Okay, this is a note. Like in this case, we have 2 eigenvalues, and now the minus 2.5 and the plus 1.5. And we're able to use the power method to find the eigenvalue near this. Right. And we're saying the power method requires fewer iterations. And when we have fewer iterations, if the magnitude of the largest value is not too close to the magnitude of the second largest one. So in this case, if these two are not too close to each other, and obviously that becomes relative, but we elaborate what we mean by that being too close. Next. We elaborate on what we mean by too close, and that hinges on sort of the magnitude of the distance between the two numbers. And we say the following: the values Right, so the values, magnitude of 2.5 and 1.5 are fairly close to each other. To each other. To accelerate convergence, we could for instance shift. We could, for instance, shift by the value s equals 2 exactly. Moreover, the eigenvalues of B would then be minus 2.5 minus 2, which is minus 4.5, and 1.5 minus 2.5, and in this case, shall discuss exactly the significance of the elaborations here as we try to understand this particular feedback, but also, and in this case, the larger one is much larger. It's much larger than the smaller one. And therefore, convergence will be faster. The values, okay, we actually mentioned the following, that the values, because we had the minus 2.5 as the eigenvalues and also the eigenvalue plus 1.5, and we're taking their absolute values, and we're then saying the values of the magnitude of 2.5 and 1.5 are fairly close to each other. So we recognize them as being fairly close to each other. To accelerate convergence, we could, for instance, shift by the value 2. So the eigenvalues of B would then be minus 2.5 minus 2. Because we have said, therefore, the eigenvalues of B would be given by what? Would be given by lambda 1 minus S, lambda 2 minus S. Those are the formulas we're using. So if we're going to use lambda 1 minus S and then lambda 2 minus S, we already know if we could, for instance, shift by the value 2, the eigenvalues of B would therefore be minus 4.5 and minus 0.5. Because we then say minus 2.5 minus 2, yeah? Minus 2.5 minus 2, because we're choosing S to be 2, suppose, And then now we have the 1.5 minus 2, and therefore we have the minus 0.5 here. Here we have minus 2.5 minus 2, which is minus 4.5. And in this case, the larger one is much larger than the smaller one, and therefore convergence will be faster. So through the method of shifting, we'll just make sure we sort of increase the sort of distance between the two eigenvalues, and if they are really further away from each other, because at this point you can see the difference between the two is just about 1 unit. But if you then, or just a little bit, because for example, this is minus 2.5, yeah, and this is 1.5, and this is 0. This is 0. So okay, so at this point, okay, yeah, then you would say the distance between them. Okay, now if this is the lambda line, okay, lambda line of values. So now you would say maybe the 1.5 there and it's 1.5 there, and you can see the distance is 1.5, and then also the negative is on that side. So you can see that it is 4 units away from each other. 4 units away from each other. But what we're able to see, if these are 4 units apart from each other when choosing the distances between them, but also you'll be able to see that even here, still these are 4 units from are still 4 units from each other, because so if you do minus 4.5, so okay, so now I would have the following. Okay, so you'd have, for example, what would the distance between these two be? Okay, so the distance between these two, you would see that it is actually what you can get when you subtract them, and then take the modulus of these. So you can then actually be able to subtract them in any random order. So you can take, for example, normally if you are looking at numbers on the number line, 2 and 5. What is the difference between the numbers 2 and 5? The biggest one minus the smallest one getting a 3. The distance between them is 3. So here I use the same, and you're going to say the bigger one minus the smallest one. And the biggest one would be what? Okay, would be a minus 0.5 minus the smaller one. The smaller one is on the left. So on the number line, minus 4.5, and this is minus 0.5 plus 4.5, and therefore it's 4 units of distance, and therefore still they are, the same distance away, these eigenvalues. These ones are the eigenvalues of B by shifting. And in this case, the larger one is much larger than the smaller one, and therefore convergence becomes faster. So sometimes we can actually obviously use the method of shifting to make sure that they are not really very close. In magnitude, the magnitudes do not look very close, because we're using the magnitudes. Right here, 1.5 is very close to, and as they said, very close to, for instance, 2.5 and 1.5 are very close to each other. And so we use shifting to make sure they are very relatively further away from each other, and through this process we're able to get the result. Okay, and so we continue as follows. We continue then as follows. Right, so now the couple of things therefore that remain very pivotal to understanding, but also we need to be in a position to solve more problems that involve further differential equations. Let us look at the following. We'll look at the following. Write down the finite difference equation. Okay, we've been discussing these theoretically. We have an opportunity to have first-hand experience of solving a partial differential equation by the method of finite differences. Once again, there are many other methods that we use to solve differential equations, but often it's very important that students are able to solve these for, end of term assessments. Write down the finite difference equation corresponding to the three-dimensional partial differential equation, this one. At the grid point xi, yi, yj, zk of a rectangular mesh with delta x equals delta y equals delta z equals h, denote u of xi, yj, zk by uijk. So, yeah. Okay. What are we supposed to do? We need to write down the finite difference equation corresponding to the partial, to the three-dimensional, because it's an ax, y, z, so it's a three-dimensional partial differential equation, but also you can see the x, y, z components in terms of xi, yj, and zk. Right, so let us solve this particular problem and solve it step by step. Right, so now to answer this question, and this is what we need to do as the answer. So now we look at the partial derivative squared of u divided by x, the partial derivative of x squared, and then partial squared y divided by the partial derivative of y squared, partial squared u divided by the partial derivative of partial z squared, and plus u plus xyz equals 0. In which case, you have u. ui plus 1. Right, so you're going to have ui plus 1 together with j and k minus 2. ui j k plus u I minus 1 j k divided by h squared. H squared. U I j plus 1 k 2 u I j k plus u I k plus u I j. Shall we discuss this? K plus 1 minus 2 u I j k plus u I j k minus 1 divided by h squared plus xi yj zk I j k equals 0. equals 0. Okay, let us discuss this here and mention the actual attributes of this. Okay, we can see that first and foremost, what we have here, we have 1, 2, 3 second order partial derivatives of u with respect to x first, with respect to y second, and with respect to z third. With respect to x, therefore, you would have the I plus 1 because the derivative with respect to partial derivative with respect to x twice affects the first component, x, which is the x, y, z. So it affects the ith component. That is why, therefore, you'd have the I plus 1. The j and the k remain the same in the first summand, but we have the minus 2ijk plus ui minus 1jk. So this becomes the formula for the d squared u dx squared. But now you also have d squared u dy squared. Now, obviously, we are finding the derivative with respect to this is partial differentiation, and therefore it is gonna affect what? It is gonna affect the middle component. It's gonna affect the y component, so that in this case, the y component, you're gonna have a plus 1, meaning that the middle component is gonna remain u ijk minus 2 of that, and plus the last one is going to be affected as well. In the same way that the third term, 1, 2, 3, the third term is I minus 1 in the first component. Why is it the first component? This is like calculus, the first principles of differentiation there. Okay, the first principles of differentiation being used towards being applied to partial differentiation for the second order equations. So at this point, then you have this d squared u dy squared, and then you have ui j plus 1 and k minus ui jk, and then you have also the j minus 1, which becomes the last component there. And okay, we are saying the middle component in the last term is the one that is affected, so that is j minus 1. Here is ui minus 1 for the x, and then it is ui plus 1 for the second ui minus 1. Here, uj plus 1, uj minus 1. Yeah, and then it is divided by h squared. In the last component, it is the kth component that is affected, which is the z component for the dz squared. So that is going to be uij k plus 1 here, and then minus 2ijk plus u ijk minus 1 divided by h squared. And then now you have this xyz. The xyz therefore becomes the xi, according to this, becomes xi, yj, and zk, plus uij. Right, so the uij you can actually write this way, and in principle and strictly speaking, the uij has to be written like so. It has to be written like so. So obviously, in view of this notation, right, of the notation, if you have a u, x, I, y, j, z, k, you write it like I said j, and k. So we adopt the notation given the question. Where we study, we're looking at the grid point, which becomes sort of the central point, xi, yj, zk, of a rectangular mesh with delta x equals delta y equals delta z equals h. Okay, so we move on. But there's a little note that we need to include here. A little note. Okay, but this is the answer to the question. So yeah, it's the answer this. We're done with the answer, but we can write a little note. And here is the little note. You need to recall or simply remember to replace x, y, and z. Also, by okay. So x, I, y, j in zk. Remember to replace the x, y, and z also by x, I, y, j, and zk. which we have done here. The x, y, and the z, we replace them by xi, y, j, and zk, which we have done. Moreover, we note that the actual fundamental difference, what you call the difference equation, right? So the difference equation always approximates the differential equation, at some grid point, and this grid point, arbitrary grid point, being some xi, yj, and zk. So all terms must be consistently evaluated at that same point. Okay, remember to replace the x, y, z, which we have done, also by the x, I, y, j, and zk. The difference equation always approximates the differential equation, right? The difference equation which we have got just here, because we are to write down the difference equation that is corresponding to the three-dimensional partial differential equation. We have written already the difference equation and we discussed it. But we're then saying the difference equation which we have written always approximates the differential equation at some grid point. Right, so we use the difference equation because it's nice and easy to manipulate. We use the difference equation to do what? To approximate the differential equation, the partial differential equation at some grid point. So all terms must be consistently evaluated at that same point. So all terms must be consistently evaluated at that same point. And we proceed to analyze this as follows. Right, we look at the second Roman figure. Okay, we're back here. Now, the notion of what we call the the first Roman figure, we've already given it enough attention, but we are looking at the second Roman figure. We've just put it up here so that we can be in a position to follow exactly and make sense of this. But rewrite the difference equation in the first Roman figure. We have written the difference equation in Roman figure 1 for the 6 marks, but you need to rewrite it. Rewrite the difference equation in the first Roman figure into an iteration formula, approximate or rather appropriate for what you call the Liebman's method. So you're going to use what you call the Liebman's method. So rewrite the difference equation in the first Roman figure. We wrote the difference equation in the first Roman figure, but need to rewrite it, need to write it again, but into an iteration formula appropriate for Liebman's method. Use these superscripts, UK plus 1, to show how new values are computed from previous ones. Okay. All right. So this is then what we do here in relation to this method that is being set here. We have seen how we wrote the difference equation, but we are going to answer this question. So this one, with the required superscripts, now we need to write the following. So you're going to write U I J K, then K plus 1. And this equals, or you write with the superscripts now, so you just put a K plus 1 there. And this is 1 over 6 minus h squared. Okay, we shall discuss the significance of this presentation. Use superscript K I plus 1 J K U I minus 1 J K U K I J plus 1 K U superscript K I J minus 1 J minus 1 K plus U superscript K I J K plus 1 plus U superscript K I J right, they say K minus 1 plus okay, this is a single plus here. Going to discuss this, please, in relation to the first difference equation we wrote for this second order partial differential equation. So we have h squared, okay, xi yj zk, right. Okay, so we continue. Okay, yeah, we're going on, but now we're looking at this presentation now, which is what they want in this question. So we want to make sense of this and make sure that everything is okay. Rewrite the difference equation in Roman figure 1 into an iteration formula appropriate for Liebman's method. Use the superscript UK and also UK plus 1 to show how new values are computed from previous ones. Right, so the couple of things obviously that we need to take into account, but we need to look at the fact that this is how we wrote the differential, the difference equation. Minus 2, so you have the middle terms, like the middle terms are the same here. Minus 2 uijk, minus 2 uijk, minus 2 uijk. So it's minus 2 minus 4 minus 6, minus 2 minus 4 minus 6 over h squared. Okay, because you have the minus 6 over h squared that is going to come from those middle terms. The minus 6, therefore, through algebraic manipulations, is actually can therefore be converted to the fact that, therefore, you would actually then make uk plus 1 the subject of the equation, and uijk, which symbolizes the fact that you have the three variables, of course, because it's three-dimensional partial differential equation, uijk, and there are three of this. And then right now you have the x, y, z, which we have xi, yjzk, and would actually therefore have our h squared. Moreover, we take note of the fact that you would have the following representations that emerge from the different equation we wrote earlier, but we're just now using the superscripts. Use superscripts to show that to show how the new values are computed from the previous ones. So you'd have ui plus 1 jk, and then we saw that from the difference equation we had a ui plus 1. We also had a ui minus 1. Yes, we had a ui minus 1. In the beginning, we had a ui plus 1. In the end, we had a ui minus 1 for this term here. Right. And then now, in the same way, in the beginning, we had a ui plus 1. In the end, we had so because we said that this partial derivative with respect to y affects only the middle component, affects only the yj. So you had a j plus 1, but there was a minus 2 uij, which we have taken care of. We have solved for it here. And then now we are left with here the j minus 1. Yeah. And then also, we actually obviously need to incorporate the k. The k is the k plus 1 and then the k minus 1, right? And then now you would therefore have the h squared xi yj and zk. But this is not the only way to do it. We indicate that it really can be written differently. So it can be written like so, but it can also be written slightly differently as follows. We can say this is the case, or ui jk k plus 1, which is 1 of 6 plus 1 jk superscript, because you need to use, we can write it like the way we did, but you can also write it like this. And then now we actually have here plus u. Okay, we know that we write ui plus 1 and then you write ua minus 1. Okay, why? Because it is from the d squared u dx squared. It affects the first components, right? Ui plus 1, ui minus 1. Then there's j and then k. Okay, and then this one. And then plus ui j plus 1 k, superscript k. ui superscript k. ui jk plus 1. Okay, we're going to check these superscripts to make sure they are the kinds of superscript we need. So the j minus 1 is just going to be j, then jk plus 1. K plus 1k plus u k I j k minus 1 h squared jk h squared ui jk. Okay, so you have this one. Okay, we can write it like the former, or you can write it like this. In which case, therefore, if you write it like that without the 6 minus h squared in the denominator, we're going to have exactly the h squared for the u and also You can have the h squared for the x, for the xyz, and we can also, in a similar manner, write it like so. But there is, once again, as I said, it's simple to remember this because it is the fact that from the difference equation we write, normally we use the former difference equation, but once again, there's a conversion to what you call an iteration formula appropriate for what you call Liebman's method. And we use the superscripts for that. And we solve for the uij, k, and then we give it a superscript k plus 1, and then the rest we give these superscripts k, because this one is the first one in the d squared u dx squared, which is ui plus 1. Then the last one is this. Then this one we've put here, it's common. That's why we factored it out, right? And as we figured it out, then we're able to do the following. Okay, so we continue. Right, we continue. Right. Okay, we continue, please. Right, we continue, but there's more. Okay, we're going to explore this in detail we shall solve a problem using these kinds of techniques. So we shall use these kinds of methods to actually solve the problem. So, right. Okay, so you understand it better. You'll understand it better. You understand it better. Okay. Okay, right. So yeah, all right. You understand it better when we actually get to use it. But there's this more little comment that we give. And this is the comment. Right. Is a side note, we say that this is what we call the Gauss-Seidel. The Gauss-Seidel type approach. Gauss-Seidel type approach. The alternative. The alternative is to use a Jacobi method where on the right hand side updated information is used. Is used when necessary. When necessary, so that for instance, we might use, for example, the ui minus 1 jk superscript k plus 1. This means the derivative, of course, so the k plus 1 in the parentheses. Or you can use ui j minus 1k k plus 1. and Uij, k minus 1, k plus 1. Instead of Ui minus 1 jk, Ui j minus 1 k, and U I j k minus 1 k. And we say either one will give you right, and we know that, yeah, we can mention that. Okay, so any of those two methods will earn you full marks. Either one will obviously will get you will earn you full marks in a question like this. So we note that either one will give you full marks there. So, but this is not the answer, but it is just a comment. We are noting that the method where we're using the superscripts, etc. This is what we call the Gauss-Seidel type approach. The alternative is to use the Jacobi method, where on the right-hand side, updated information is used when necessary. So that, for instance, we might use the U subscript I minus 1 jk superscript k plus 1, and then j minus 1k, and this one here, instead of ui minus 1 jk and j minus 1k and this one. Either one will earn you full marks. So in other words, this is not the answer. The answer is the one we wrote earlier. But this is what you call the Gauss-Seidel type approach, which uses the superscripts. This is the Gauss-Seidel type approach. The alternative is to use what you call the Jacobi method. So either we use the Jacobi type or the Gauss-Seidel type or the Jacobi method. Right, and when we use any of those, so that, for instance, we might use the UK plus 1, I minus 1 JK, and now you use the I minus 1, you use J minus 1, you use K minus 1, instead of the I minus 1, J minus 1, and K minus 1. What is the difference? We might use the K plus 1 powers instead of the k powers. That is what we are saying here. So for the I minus 1 jk, we might use the k plus 1 powers because we chose to use the k powers for the plus 1, I plus 1, j plus 1, j minus 1. We use the k powers, but we might decide to use the UK plus 1 powers instead of the k powers. Right, and once again, any of those is just a variation in the notation. It is not at all supposed to be different at all. So each of these presentations, if the student is gonna be using k plus 1 here instead of k, we agree that it is the same thing. Or you actually obviously decide here, oh, okay, instead of the k plus 1, instead of k's, I'm gonna use wherever there's k, I'm gonna use k plus 1. And so that is going to earn you full marks. So if you decide, for instance, you can actually vary these, and that's what we're saying, and use k plus 1 in the place of the k's. So it is accepted as equivalent. Now, we want to continue to explore. Okay, what have we done? Okay, we have rewritten the difference equation in the first Roman figure into an iteration formula appropriate for Liebman's method. Okay, we're gonna We're going to explore this Lippmann's method in detail. Even in our subsequent discussions, we have put plans in place to make sure we explore this Lippmann's method. It is a method that must be celebrated, but must be understood very much. Okay, because this method is examinable, please. Lippmann. As much as the finite difference method we're going to discuss now is examinable, but yeah, we continue. We continue. Our next approach right now is going to focus on the rectangular square problem. The rectangular square problem. And this rectangular square problem is very, very important for us. But we're saying the equation d squared u partial derivative squared of u with respect to x squared, partial derivative squared of u with respect to y squared equals 0 is to be solved in a rectangular region. Is to be solved in a rectangular region. Is to be solved into a rectangular region. The grid delta x delta y equals 1, the boundary values and the numbering of the node points are given in the sketch below. Okay, in B we need to solve. Right? And we're going to show how we solve problems using the methods of length and also using some of the methods like what you call the ADI method. But now we are saying we have been given these homogeneous differential equation, right? Which is given in the form d squared u dx squared plus d squared dy squared equals 0. Is to be solved in a rectangular region. The grid point delta x delta y equals 1. Okay, there's a grid where the change in x equals change in y equals 1. The boundary values and the numbering of the node points are given in the sketch below. Numbering of the node points, right? The nodal points. And now you can see there is a U1, there is a U2. There is a V1, there is a V2. So these U1, V1 are the same point, right? And then you have, for instance, your U equals 1, which is the vertical, and then there's u equals 1 that appears as the actual length of this particular region, and there's also u equals 0, which is a boundary condition. There's a boundary condition that says u equals 3. Now set up, that is the question, set up the two sets of equations for solving the values of u at the 4 node points by the ADI method. Use the notation of the sketch with function values denoted by ui in row-wise traverse, right? And by vi in column-wise traverse. Let us look at the row-wise traverse versus the column-wise traverse, right? And we will obtain, hence, the following results. Right, so the couple of things that we need to take into account here as we focus on this problem, because it requires a lot of writing, we take note of the following. We're looking at the B first Roman figure, and we're going to discuss this in detail. Let's look at the row-wise. The row-wise. And then we shall look at the column-wise. So looking at the row-wise, we apply the equation. The equation UL. U0. Which is UR. Two V0 minus VB. Shall I explain this? Right, minus VB. So we shall apply this equation, but when we use this equation using the row-wise approach analysis, we shall use this row-wise analysis at the nodes. right, at the nodes, right, at the nodes, for example, right, at the nodes U1, node U1, U2, U3, together with U4. Right, so you have U1, U2, U3, U4. Those are the nodes that appear in this particular rectangular region. Right, so if we do that at those nodes, we said that we shall, when we look at the rectangular region, looking at the row-wise approach, you apply the equation. This one, UL minus 2U0 plus UR. And what is this here? It is actually minus VA plus 2V0 minus VB at the nodes. One minus 2U1, U2. Okay, I'll discuss the significance of these and how we obtain these from that equation. So you have 2V1. We're looking at the row-wise approach, and we'll discuss how we get to these particular equations. Right, and then you'd have, for instance, U1 minus 2, U2 plus U3 plus 3. Okay, the 3 is coming from the boundary condition. Minus 1 plus 2V3 minus V4. Shall discuss this. 1 minus 2U3 together with U4 minus V1 plus 2U2 plus 2V2, right, plus 2V2, and this is 0 row-wise. So we're taking the rows here, and then we're going to discuss that. So we have U3 minus 2U4, 3 minus V3, 2V4. So that in the end, we would actually write the matrix equation that is going to arise out of this. And what is the matrix equation that is going to arise out of this? This is the matrix equation that we're going to get. So we're going to get the following. Before we look at the column-wise, okay, I want us to, we're first discussing the row-wise. We're going to discuss how we get to these particular equations first at the nodes. And then we shall have exactly the following. So you'd have, for instance, minus 2, 1, 0, 0. And then you have 1 minus 2, 0, 0. 0, 0 minus 2, 1. 0, 0. 1 minus 2. U1. U3, U4. Okay, I need more space here. I actually need a bit more space. But let's first discuss this before we actually continue with our elaboration. So at the nodes 1, 2, 3, 4. 1, 2, 3, 4. Let's look at the node U1. Right, at the node U1, for example, we're able to see here is the node U1 there. Right, so but now we note that at this point, if we then say that the grid delta x is equal to delta y equals 1, right, we're able to make the following observation that if this is u equals 1, u equals 3, 1 and 0, we're able to realize that using this particular row-wise approach, UL minus 2U0 plus UR minus VA. So let us look at this. So if you look at the node U1, this one here, you're going to have exactly 1. You're going to have, because there is associated with these, you can see, looking at the row, looking at the row, you'd have a 1 and then minus 2 U1. We were at the node U1, so you have 1 minus 2 U1 there. And then you have plus U2, which is this one. And then this is actually exactly equal to, right. So what is this exactly equal to? Once again, we look at what we've written here. So it is the negative of VA, right? So if it is the negative of VA, we're able to see precisely that the negative of VA becomes the negative 1. And also 2V1. Right, and obviously that would be the V's. Right, so if you look at the V's here, because we have the U's and they relate to the V's. Right, and so looking at the V's, you'd have a 2V1. Right, so if this is the middle one, of course, you have the correspondence here, the U1 and the V1. And so if you look at it, therefore, it's going to be plus 2V1. Then you would have minus V2. Right, and if you look at V1 together with V2, they occur in a vertical position. Right, because they occur certainly in a vertical position, you would therefore have that the V1 is here, the U1, this is exactly a U, because it is exactly a U equals 1, it therefore occurs as what? It therefore occurs as a minus 1. Right, now the reason for that would be, if you look at the V's themselves and their positions, they occur vertically. So you'd have, for example, a U1 here, rather a V1, a V2. And if this one here, for example, is a U equals 0, and you have a V1 and a U2, rather a V2, that's what I mean. And therefore you'd have a minus V2 there. Okay, there are more details we're going to give in this particular case. But also, if you look at the U2 center point, right, if you look at the center point U2, let's relate to that quickly. Right, center point U2, you'd have U1, for example. You would have, if this is U2, you'd have U1 that appears here towards the left. And then it's always minus 2 from the difference equation we've written first. And then obviously, I want us to then say, now, if you proceed, we have written the U2, minus U2 always. But if you then continue now, if you look at the U2, what are you able to see there? On the left and the right. So you'll be able to see that on the left, it's U1. On the left of U2, it's U1. And on the right of U2, it's what? Okay, it's a 3. That's why you have the 3 there. And I want us to first finish this particular part here. Let's look at U3, left and right. Right, so U3, this is the one. What do you have on the left? Obviously, you would have a 1 on the left, and also on the right, you would have exactly a U4. Right, and obviously, that is why we have the plus U4. Let's look at U4, for example. Right, if you look at U4 here, what do you have U4 on the left and the right of it? Right, so on the left of it, U4, we expect a U3, which is there. And obviously, if U4 on the left is U3, but the right of it becomes exactly a 3. And we've seen the 3 there. Right, now, obviously, we've seen how we're able to look at the left and right. You're looking at the row-wise approach there. But simultaneously, if you look at the U3, you're able to see certain positions. Let us look at the V's. Okay, let us look first at maybe one specific equation, the bottommost equation. Right, the bottommost equation is going to have a U3. Let me just write it here. I want us to have this discussion with one specific equation. Let us look at the fact that we are saying U left minus 2U, the one at the center, and then plus U on the right of the central point, center of to the right of the node we've chosen. It must be equal to minus VA plus 2V0. So we're going to look at V0. V0 becomes the node relative to V, right? And then also minus VB, right? So, and obviously now this becomes relative positions. So if you look at these horizontally, okay, right. Okay, let us look at these quickly. We actually have said already, for this particular one, I want us to look at, for instance, U4, which we have written on the other side, but let's analyze it here. So you'd have, for instance, a U3 minus, we're looking at U4. So you'd have 2U4. On the left of it is U3. Well, because the center point, if you choose the center point to be U4, the left is U3. But the right of it becomes U equals 3. That is the right. Next. Okay, right. Now, if you look at these will be related to what? These will be related to the center point V4. So you'd have 2 V4. Because the U4 is the node, but it goes with V4. Okay. Now, this would go with minus V3 at the top. Right, minus V3 at the top. And it goes with what? It goes with, if it goes with minus V3 at the top, at the bottom, we are able to see that we have 0. So this is going to be actually exactly a minus 0. Like a minus VB is going to be a minus 0, but it's minus there. But we can see the top is minus V3 and then the bottom is that. Okay, we'll analyze just one equation. The truth is the analysis of the rest of the U1 center point, U2 center point, and the U3, U4 are the same. Now, from the equations we've written, we have the following, yeah? Okay, we shall discuss this. We have minus 2, 1, 0, 0. And then we have 1 minus, we're just factorizing. 0, 0, 0, 0, minus 2, 1, 0, 0, 1 minus 2. And then U1, U2, U3, U4. Okay. Okay, from the equations I've just written now from the grid, rectangular region, we have 2V1. We've seen on average, we just analyzed an equation, minus 2V2. And then we have 2V3 minus V4 minus 4. Okay, we are taking it from what we wrote now. Minus V1 plus 2V2 minus 1. And then we have minus V3 plus 2V4 minus 3. Okay, this minus V3 plus 2V4 minus 3 is what? It's those are the equations that would arise exactly from this particular equation that we've written. And I want us to analyze this actually in some very, very good detail. Right. Okay. There's something more I want us to say here. Right, there's something more. Okay, yeah, good. Okay, now look at these and think of these very carefully. But also the fact that these particular equations we've written have now been written like this. But also, we are looking at the fact that in these particular equations, we seek to write this matrix equation in simplified form. So if this is the case, for example, what would this mean? This means this column is U1, U2, U3, U4. So there are zeros here that appear. Let's look at the first equation. Minus 2, 1 for U1, U2. Right, so you'd have for U1, it's minus 2. For U2, it's 1. But, so now you'd have therefore that U3, U4 are 0 here. Okay, so That is why you have the zeros. And then you would have the right-hand side. But you have the number 1. Right, so this number 1, you move it across. There's a -1 here. So if you move this number 1 across, what is it going to give us? It's going to give us a -2. And hence we have the -2 here. But now when we have the -2, you would have 2v1 and also minus v2. 2v1 minus v2. 2v1 minus v2 minus 2. So, all right. So we get the, okay, this is sort of the answer we're getting. But okay, I'm moving like this because I want us to actually make more sense of this before we finish. I want us to look at the column-wise. Okay, that was the row-wise. So we look at the region again, but we're looking now at the column-wise. Column-wise, what equation do we apply in terms of the ADI? We apply the equation. Okay, we apply the equation. This is the formula. So it becomes VA 2V0 center region, center nodal point or node point, VB, which equals minus U left for the column wise. So now we are looking at the vertical things. And then we have the U left to U center minus U right. Okay, at the nodes. Right at the nodes. At the nodes. What are the nodes for the V's? They are V1, V2, V3, V4. Okay. Let us analyze this and practice together with the nodes. Let us take 1 point. Let us take V1 first. Okay, we choose V1. Right, so if we choose V1 and we're going to use what equation for this one is row-wise. Okay, let's just look at this quickly. We're concluding. This one is row-wise. And now we're going to look, this is the formula for row-wise. Then there's a formula for column-wise. Okay, what is this column-wise thing? So it's going to be exactly VA minus 2V0, which is minus UL plus 2U0 minus UR. Sorry. Okay, now you would have this column-wise. Let us look at a center point. Okay, we're looking at V1 as our V0, like our center point. So we look at V1. Column-wise, so we're going to have what? So column-wise, we're looking at things vertically, so you're going to have first 1 minus 2V1. So we're looking at this one, but top of it, we see there is a 1. Minus 2V1 is always minus 2V1 according to the difference equation. Plus, the V2 is becomes the V that's directly below that, and it is a V2. Equals. Now we're going to look at the U's. The U's is minus U left. Right, U left. Now, if this is the center point, what is the U on the left? So the center point for the U is, for instance, plus 2U1. But the left is minus 1. And then the right is what? The right is the U2. The right is the U2. Okay. So now, because we can see the U2 there, it's minus the U on the right. It's minus U2. Okay, now let us write all these things here. So in other words, corresponding to the V1, V2, V3. So the first one is V1. We've written it. Is minus 2V1. V2. Minus 1 plus 2U1. U2. V1. 2V2. 0. Minus 1. Plus 2U3. U4. 1 minus 2V3. V4. minus u1 plus 2 u2. Okay, I'm just moving because I want us to finish these things. Otherwise, we'll just look at the diagram for the whole day. And then this is v3 minus 2 u4 plus 0. Boundary is minus u3 plus 2 u4 minus u3. Okay, we've written it like this. And then next we actually like perform some additions. Like what we're going to do is we're going to move some of the numbers. The number 1 is going to move to the other side, giving us a minus 2. And then we have 2v1, v2, v3, v4 columns. V1, but here we'll have minus 2 and 1 for the V1, and then the rest will be zeros for the for the V3 and V4. There are no V3, V4 in the first equation. Okay, so now by dint of that, so I'm just writing these things so that you can make sense of them. I want us to make sure we have all the things we need. All right, so we said already it's going to be minus 2v1, v2 is 1, and then 0, 0. Why 0, 0? Because there are no v3, v4. But this one is going to be moved across because the constant moved to the other side, giving us a minus 2, okay? And then with that in mind, these are the V's. So this is actually a V1, a V2, a V3, a V4. And then now you have a 1 minus 2, 0, 0. And then you have 0. Okay, we're taking those equations, please. We're putting them in matrix notation. We're just factorizing. 0, 0, 1 minus 2. Obviously, I explained why this is minus 2, 1, 0, 0. The explanation for the rest of these becomes similar. Now, let us look at this top equation as I was saying. This is 1. We move it across. It becomes minus 2. Then it becomes what? We're going to write 2u1 minus u2 minus 2. 2u1 minus u2 minus 2. The rest will be the same, right? We'll just write everything out. So we're going to write here, we said we're going to write 2u1 minus u2 minus 2, and then you have 2u3 minus u4 minus 1. You have minus u1 plus 2u2 minus 4. And then we have minus u3 plus 2u4 minus 3. Okay, that is what we have got. But now, therefore, this is the answer to this particular question. What have we done here? We have answered this question. What is this question? We have answered the first Roman figure. What is the first Roman figure? Right, the first Roman figure says, set up the two sets of equations. Two sets of equations for solving the values of u at the 4 node points by the ADI method. Right, use the notation of the sketch. Right, and with function. Right, with function, values denoted by UI. Right, by UI. In row-wise traverse, we did the row-wise traverse, right? And then, right, we continue. There's something more I want to say. So there's something more I want to say. Okay, now this ADI method is a very, very important method. This ADI is a method that stands for the alternating. It stands for the alternating direction implicit. Alternating direction implicit. Alternating direction implicit. Okay, so that is what we have. Alternating direction implicit, and we say it is namely ADI method. Okay, we have looked at this method, but before we conclude our discussion, I want to mention the following. I want us to discuss part B. I can see we've gone beyond the time by some minutes, but explain how you would proceed to solve the problem by using the ADI method. You need to explain. They did not say solve it, okay, because it's long. It's just matrices that you can, use to solve. But they're saying explain how you would proceed to solve the problem by using the ADI method. Please don't solve it. Just give an explanation. That's what the examiner is saying. Please just explain. That's all. And this becomes the explanation. So we're going to explain that before we conclude our discussion so that we can be both at ease. Right, so we are looking right now at B, second Roman figure, for the explanation of that. So now to explain, we start with a first guess. Right, a first guess in the way we use we do with the Jacobi and the Gauss-Seidel. We're going to discuss these at some point. There's some smaller problems we shall solve, but this one is relatively large. But obviously, even in this question, they actually now did not want you to solve this particular question, but they wanted you to explain. So we're explaining just now. We're explaining just now. We are surely explaining just now. Right. Okay, just 1 second, and then we are finishing this discussion. We're going to discuss the right. All right, we are continuing. We're finishing this discussion, please. Okay, I want us to discuss the following. So what you need to do is to start. Okay, you need to start with the first guess. It V0. The other, okay, start with the first guess. This V is called V to the power 0. Okay, we're discussing how we explain because it's very long. It's big matrices we're dealing with. Right, start with the first guess. V we call V to the power 0. Okay, so call V this one, the vector. The vector V10, V20, V30, V40, like that. And then next, as part of our explanation, you need to repeat. Okay, what do we repeat now? We repeat like step 1. You need to solve UI from star. Solve UI from star using VI minus 1 on right hand side. Solve VI from double star. Okay, I will explain the stars. So the stars are the fact that this one here is a system that's going to be double star for V1, V2, V3, and V4. We saw that this one is for the V's. And then this one is for the U's. This is the first star for the U's, U1, U2, U3, U4. So solve UI from star, the first one for the U's, using V to the power I minus 1 on the right-hand side, and solve VI from double star. All right, so from double star using on right hand side. Right hand side until the change. So you repeat these processes. And we're going to do some examples, please. But not in our next meeting. Until the change vi minus 1 is less than, right, it's less than some given. Normally, they must give some tolerance, some given tolerance, some given tolerance, right, tolerance. Okay. So, yeah, this is the explanation. But there is also a little note that we need to emphasize. We note that in B, for example, okay, because we in B we actually in B Roman figure 1, that is where we wrote those particular column-wise, row-wise, systems. So we note that in B, first Roman figure, we did row-wise, column-wise here. You must write down. You must write down the equation. You must write down the equation for this particular problem. Right. So we have seen already. Know that in B Roman figure 1, we did row wise, column wise thing. You must write down the equation for this particular problem. You must write down the equation for this particular problem, which is what we've done. And moreover, we are saying it is never enough, because somebody can, obviously, this is common knowledge, but it is not enough to just state the general equations. Okay, because somebody can say, I'm going to give the general equations for the column-wise, row-wise, and stop there. But now you need to use the grid there, the nodes as well, to find the actual equations from the given rectangular region and write them in matrix notation. Right, and in particular, by so doing, and so this would conclude the note we've given. This is the solution for the part B, where you say start with the first guess. And this, you just explain how you're going to use the ADI method to solve the problem. But you don't have to solve the problem because it's so big. Because what is the size of this? 2, 4, 2, 4. You have 4 by 4 matrix to solve. Obviously, this is quite possible to solve. But yeah, it's the 4 by 4 matrices are a bit large. But I wanted to also then say we have solved this particular problem here. That was like, given the differential equation with this particular rectangular region, this one, set up 2 sets of equations for solving the values of u at the 4 node points by the ADI method. We've done. Column wise is VA minus 2V0 plus VB equals minus UL plus 2U0 minus U right, UR. And then we went on to look at the row wise, which starts with U on the left, U left minus 2U0 plus U right, which is minus VA plus 2V0 minus VB. Use the notation of the sketch. We use the notation of the sketch in terms of the U1, V1, and so on, with function values denoted by UI in row-wise traverse, and by VI in the column-wise traverse. We did the column-wise traverse with the VI, but we have done that. We have used the matrices. Explain how you would proceed to solve the problem by the ADI method. The marks were totally 14 for this question, but please, you did not have to solve this particular question. I think that at this point, it was very, very interesting having this discussion here. And we actually obviously will be continuing our discussion, looking at many problems that pertain this, both the ADI method, the finite difference method, and other methods like the Liebman's equation. Right, the Liebman's method would also be used here in terms of rewrite the difference equation Roman figure 2 into an iteration formula appropriate for Liebman's problem, Liebman's method. So You would have to use the Leibniz method. But at this point, I think I must thank you so much for joining us. It's awesome having this discussion. I know very well that there's always much to learn. And the truth is that we must actually be in a position to continue with our discussion even in our subsequent meetings. And now, if you are to check very carefully, we actually have another discussion to have. Let me see. I think that'll be tomorrow. And then tomorrow we'll continue seeking more understanding. Right. So we'll have also a meeting tomorrow at 12. At 12. Right. So yeah, we should have a meeting tomorrow at 12. Saturday, 12. Right.
Thank you so much.
Yes. Okay. Thank you so much, dear. Okay, I was just looking at the schedule there. Okay. Right. I must thank you so much for joining us. We shall meet tomorrow at 12, and then we shall be going into detail. I must indicate that we've finished a paper, right, and more. This paper we're discussing, this one, was the January paper. It was the January paper, right? It was the January paper of this year, February. Yeah, January, February, supplementary paper that was. Okay, so yeah, thank you so much for joining us. We shall meet again tomorrow at 12 p.m. Thank you, take care, and goodbye.
Thank you, bye.
Thanks, goodbye.